Okay, in this video, I want to talk about common mistake in proving, right? For example, I borrow the question from worksheet UNE2, question 6, all right? The question says, prove that px squared plus x plus 2px plus p plus 1 is 0. This one always have real and distinct roots, okay? For all non-zero values of P. What does the question says, right? The questions want us to prove that whenever we pick any P, as long as P is not zero, right? The result of the equations will be some equations that have real and distinct roots. Okay, that means the equations, when you plot, will always cut the x-axis at 2 points. It can be cutting like that, it can be cutting like that, okay? It can be cutting like that, anyway, right? So basically, but the thing is, there will be no other values of P that will make it into something like this or something like this, okay? For all P, as long as it is not zero, we want it to be the case when the curve cut the axis at 2 points, okay? By the way, why must be non-zero? Yeah, because I think for simple reason, if P is zero, you don't have a quadratic equations, right? When P is zero, then the first term, the one that I circle in green, disappear. So you don't have quadratic equations. So in this case, for this particular questions, there's a mention that P cannot be zero. Okay, notice the first step is correct, right? You think about the conditions. The nature of roots, which is the real and distinct roots, will correspond to discriminant to be positive. That one is very good. Okay. But this is something that is to be proven, and you can't assume it happens. This is very important in proving, right? If you assume it happens, basically you are not proving it. You are assuming it. Okay? That's not the case. And when we assume it, basically because we want to use it to help solving a problem. But here we are not solving any problem. Okay? We want to prove the fact that discriminant will always be positive regardless the value of P. Therefore, when you work on discriminant, you can't write bigger than zero as part of the working. Okay? If you do that, you have been assuming that this happened. And that contradicts with what we are trying to prove. Okay, so where do we start? We want to prove discriminant, right? So let's start from discriminant. Write down discriminant expression to be 1 plus 2p squared minus 4 times p plus 1. Okay, by the way, I didn't discuss much, but I assume you know how to collate the terms over here, right? To make it into ax squared plus bx plus c is 0. Okay, so combine like terms, so you get that form. Then you can identify what is the a, b, and c. All right. Okay, so with that, after you write that, right, then second line makes sense, right? Because we continue, you expand 1 plus 2p become 4p squared plus 4p plus 1. Then you multiply 4p times p plus 1 become minus 4p squared minus 4p. In the end, the result is 1. Okay. Now notice, discriminant is a function of p, something depending on p. But as the final result you get, the p disappeared. It becomes constant. So regardless the value of p is, the discriminant is always bigger than 1. Sorry, discriminant is always equals to 1. Constant functions. Okay? So this is not shown yet. All right? You need to conclude first. Okay, this is the first conclusion. The first conclusion. The discriminant will be bigger than 0 for all real values of p. Okay, so this is a very important statement. You put for all real values of p is not because of just to make the statement become beautiful. No, This is a very important quantifier, okay? Because basically, you are making a strong declaration that discriminant is constant, one, regardless the values of P is, right? Therefore, you can conclude that the equations will always have real and distinct roots for all non-zero values of P. Make sense? Yeah, of course, over here, you can also put all real non-zero values of P. That one doesn't matter, okay? Because like the non-zero again, because of the context of the questions, right? The question that doesn't allow P to be zero, but that's not always the case for others, okay? Do practice on proving, right? And basically remind yourself when you do proving, have I assumed what I want to prove? Okay? If I have, meaning you have made a mistake. And again, this mistake is a good mistake because this is something that will lead you to understand what it means by proving, see distinction between proving and solving, and then learn the correct way of writing your reasons in the proving. What's the boundary? What's the container? Okay?